So chapter 10 has been all doom and gloom and air pollution and recognizing what the issue and the problems at hand are with air pollution. So now let's talk strategy. Let's talk about some ways that we can control air pollution. So historically, we had a very interesting approach to controlling air pollution. The motto was dilution is the solution to pollution. Which cracks me up. It's long characterized our main approach to air pollution control. So the idea was if you want to get rid of air pollution, build really, really, really tall smokestacks. That way the pollution is further from the surface of the earth and it gets dispersed a lot faster, and then you can't detect or trace the source of that pollution. This is equivalent to sending all of our garbage out into space. Eventually, or throwing all of our garbage into the ocean, eventually it's going to come back to get you. It's not a long-term solution, and it's certainly not a long-term solution considering our global industrialization. You can't just dilute the smoke and get it higher off the surface of the ground for it to actually go away. What we need now are to find different strategies for pollution control rather than for dilution. So I don't think anybody would disagree. The best strategy for reducing air pollution is reducing the production of air pollution. So secondary to that, we can also capture pollutants from effluent after burning. So these are strategies. If we can't reduce production, we can at least reduce pollution going into the air. The first is particulate removal, and that involves filtering air emissions. So essentially what you're doing is you are sending this gas through a mesh filter, and it can be spun glass fibers, cotton cloth, it can be asbestos cellulose, and these are industrial air filters, and they generally act like a giant vacuum bag cleaner, trapping all of those particulates. We can also use electrostatic precipitators, and those are used more commonly in power plants, and on the next slide we'll talk more in detail about what that is and how that works. Sulfur removal is important because sulfur oxides are among some of the most damaging of all air pollutants, not only in terms of human health, but also we talked about the effects of acid precipitation. So if we were to switch from soft coal, which has a high sulfur content, to a coal that has a lower sulfur content, that's one of the surest ways to reduce sulfur emissions. However, we're stuck using high sulfur coal often for political reasons because it's cheap. Sulfur can be extracted after combustion with catalytic converters, which will oxidize or reduce sulfur in effluent gas, so the gas that's coming out as a result of combustion. Residues that you capture after that sulfur collection can be elemental sulfur, sulfuric acid, and ammonium sulfate. These are things that if a company is looking to strategically make the most money possible, if they're getting a fairly pure capture of these sulfur products, they can actually then sell those. So instead of having waste, they have a marketable product. It's tough to get the markets right to where they're actually making money on that though. Nitrogen oxides are reduced in both internal combustion engines as well as industrial boilers. And the way we reduce these is by carefully controlling the flow of air and fuel. So we use what's called stage burners, which control the burning temperatures and the oxygen flow, and that really prevents the formation of nitrogen oxides. Catalytic converters on your car also help to do this, and they use platinum, palladium, or rhodium catalysts, and this removes 90% of the nitrogen oxides, hydrocarbons, and carbon monoxide that would have come out your tailpipe at the same time from your car from the combustion of gasoline. So these are amazing ways to capture or prevent nitrogen oxides in the environment. Hydrocarbon controls mainly involve the complete combustion or the control of evaporation. So hydrocarbons and volatile organic compounds, VOCs, are produced by incomplete combustion of fuels, which we talked about a couple sections ago. It's also produced by solvent plastic manufacturing, printing, other industrial processes. So if we can make sure that we have closed systems, and we're not getting an escape of fugitive gases, we can reduce a lot of these emissions. And we talked about fugitive gases being non-point source contributors of air pollution, so tightening up those leaky joints. Electrostatic precipitators can remove 99% of unburned particulates from the air. So the way these guys work is you take your particle-laden gas and you are going to send it into the electrostatic precipitator, and we have those electrodes, these plates. And what these plates do is they transfer a static electric charge to the dust particles and the smoke particles and whatever particles are in that air, that gas that you send through them. So then they take on a charge. Well, those charged particles are then attracted to an oppositely charged plate. So say they take on a positive charge, they're going to be attracted to a plate that has a negative charge, and they're going to stick to that plate. All the while, the air is flowing through this precipitator. It gets clean. So all those dust particles come out of the air, and the air that comes out is clean flue gas. It only has 1% of all the particulates that it had before it went in. Once the gas is shut off and the air is no longer flowing through there, you can take these plates and turn off the charge. When the charge is turned off, they're no longer stuck to the plates by charge. The dust particles fall, and we get what's called fly ash. Now, once these are shaken off the plates and we can remove them from the precipitator, we can collect them. They can either be reused or disposed of. Most of the time, though, they're going to be disposed of because they have mostly hazardous waste. The particulates you're collecting are mercury, lead, arsenic, a lot of heavy metals that would be considered hazardous waste, and it gets sent to the landfill to be buried. The only drawback of this guy is he uses a lot of energy, but you have a little bit of give and take. You have a lot less air pollution and particulates going into the air. Clean air legislation is controversial, but it's extremely successful. So the 1963 Clean Air Act, as it was first written, was the first national legislation in the United States. It was aimed at air pollution control, and it was not without its faults. The approach was uneven. It was difficult to enforce. So in 1970, there was an extensive set of amendments, which we already talked about, that essentially rewrote the Clean Air Act. The amendments, as we talked about before, identified the criteria of pollutants, and they also established primary standards. So the primary standard was the intent to protect human health, and it also has secondary standards, and these were to protect materials, crops, climate, visibility, and personal comfort, so humans first approach. In 1990, there were more amendments added, and these include major changes in incentives and rules for additional pollutants. So in 1990, we saw the establishment of new controls for ozone-depleting CFCs because we discovered in the 80s what that was doing to the ozone. New rules for the controlling of emissions of benzene and chloroform and other hazardous air pollutants. And also requirement that comprehensive federal and state standards be set for both industrial and transportation-based sources of common pollutants. The 1990 amendments also provided us with incentives and rules to support the development of alternative fuels and technology. And it also established the EPA's right to fine violators of air pollution standards, which was new. Another strategy for air pollution control is called the cap and trade approach, and the 1990 revisions of the Clean Air Act created this incentive as a control measure. So what happens is the EPA sets this maximum emission level for a particular pollutant, and then a facility can buy or sell emission credits or permitted allotments of pollutants. So it's up to the company now to decide, is it cheaper to install a pollution control measure or equipment, or is it cheaper to simply buy someone else's credits? We do know that cap and trade has worked very well for sulfur dioxide. When this first began in 1990, economists estimated that eliminating 10 million tons of sulfur dioxide would cost about $15 billion per year. When this was left in the hands of companies in this cap and trade approach, they were looking to find the most economical way to reduce emissions. And so what they were able to do is to reach clean air goals for 1/10 of the price. So they're able to do it much cheaper than what was predicted. A serious shortcoming of the approach is that while we have an overall pollution reduction, we still have some local hotspots for air pollution where the owners in that particular spot has found that it is much cheaper to pay someone else to reduce pollution. So they would essentially buy a pollution credit rather than to prevent the pollution themselves. So you do have a hotspot or a place where you may have more air pollution. But for the most part, it's been really successful in reducing sulfur dioxide emissions, and it's the approach that we've also adopted for CO2 emissions as well as mercury and other pollutants.